Very good day to one and all present here today. I am Gautham Ramchandran, and today I will be presenting on the topic Assessing Environmental Impacts of Aviation on Connected Cities via Environmental Vulnerability Studies and Fluid Dynamics, an Indian case study. In a fast developing nation such as India, there has been an increase in the dependence on air travel as a means of communication. Two well connected cities in India are Chennai and Bangalore. In this paper, we will discuss how aviation related factors influence the environmental vulnerability of the two cities, uh, how passenger comfort can be included in the study using complex computational fluid dynamical studies, which is the first of its kind to be performed. As you may observe, Chennai and Bangalore are two cities in the southernmost part of India. The flight time between Bangalore to Chennai or vice versa is 45 minutes or so. There is a rising need for better connectivity between two cities, Chennai and Bangalore. Uh, this is because Chennai is the center for trade and manufacture in the country, whereas Bangalore is a software hub. The demand for better connectivity has not been fulfilled completely by roadways as well as railways. Uh, Consequently, there has been an increase in the frequency of flights observed between the two cities. Up to 17 non-stop connecting flights are present today between these two cities. Development has risen at a very fast pace in Chennai and Bangalore cities, being the hubs that they are. Here we observe the two images for Chennai and Bangalore airports respectively. In the past few years, they have undergone rigorous renovation to accommodate the increasing passenger traffic. According to available data, the passenger traffic trends at Chennai from a period of about 20 years or so has been on a constant increase, as you can see from this graph depicted here. A similar trend has been observed for Bangalore as well for a period from 2005 to 2012. This rising passenger traffic trend observed in both cities has resulted in an increase in the number of flights between the two cities, which has adversely impacted the environmental health of both these cities. This thus calls for an environmental impact assessment in order to examine the city's health due to the influence of aviation. This study delivers precisely this by using a modified environmental vulnerability index incorporating aviation related factors and which is depicted as a screening tool in this study. An increase in the number of passengers traveling by air has resulted in passenger comfort being an important factor which airlines have to keep in mind. India, as many of you might know, is a monsoon driven country. We have the southwest monsoon for about 3 months of the year, whereas Chennai in particular bears the brunt of an additional northeast monsoon for about 8 to 10 weeks. Uh, During this monsoon season, flights can be extremely uncomfortable due to accompanying turbulence. Turbulent weather nowadays can be predicted up to 5 days in advance by using state of the art software such as large area simulation models LES, as well as weather forecasting models such as the WRF. In this paper, we see the direct application of CFD to quantify passenger comfort in various differently sized aircraft and try to assess how a change in the size of the aircraft or the number of aircraft can impact environmental health of the two cities. This is the first of its kind anywhere in the world. Originally, the Environmental Vulnerability Index or the EVI was designed to quantify the vulnerability of a country or large bodies to environmental factors. There are 50 original factors used for this query quantification. This original existing version of the EVI has been modified in the study to accommodate aviation related parameters. The degree of vulnerability with respect to each indicator has been quantified as one as very highly resilient or least vulnerable to 7 which is the most vulnerable. 7 out of these 50 given EVI indicators have been identified and used for this study, which have been influenced by aviation related factors as we show later on. As I mentioned earlier, the original EVI was proposed for large scale countries. However, quantifying the EVI of an entire country suppresses regional impacts of vulnerability within cities or states. Human interference has increased to such an extent that uh, there are many variations occurring between the environmental vulnerabilities of two nearby cities. There is thus a need to quantify this effect by downscaling the original EVI, as shown in the following slides. In this table shown here, 7 EVI indicators have been identified out of the original 50 mentioned, which have most been impacted by various aviation related parameters. Here we take the original definitions of each indicator as given in the handbook and calculate the various EVI scores for Chennai and Bangalore cities respectively. In the table shown above, we see the various EVI scores as calculated from the previous table. These AVI indicators are then ranked according to how they are influenced by aviation related parameters. These aviation parameters are given on the columns, namely fuel consumption, aircraft noise, etc. And the X marks indicate whether they have a direct influence on each and every one of the EVI indicators given on the left. The final score shown by the multiplication factor is the number of aviation indicators influencing a particular EVI indicator. For example, all 6 aviation parameters influence population growth, which is an EVI indicator, and thus the multiplication factor assigned was 6 out of 6, which is 1. The final modified EVI is calculated by multiplying the various multiplication factors obtained previously along with the EVI values for Chennai and Bangalore for the various EVI indicators. These scaled EVI scores are then added together to give the final scaled Chennai and Bangalore EVI scores respectively. There are some telling implications of performing this modified EVI analysis. By reducing the impact of the aviation factors, we observe on the EVI indicators, we observe that this reduces the environmental vulnerability of the two cities. One possible way of achieving this is by reducing the number of aircraft operating on the route. This is possible by replacing a large number of small sized aircraft with a fewer number of larger aircraft. This will ultimately lead to a reduction in the other aviation related parameters such as aircraft noise, operating costs, ticket prices, etc., and ultimately results in the reduction in the impact of most of the aviation factors on the EVI indicators. This ratio of smaller aircraft to be replaced by the larger aircraft along this particular Chennai-Bangalore route is discussed based on passenger comfort. This is done by fluid dynamical studies as shown in the following slides. In this section of the study, we introduce the aspect of human comfort in air travel. In order to understand the relevance of turbulence in commercial flights, it is necessary to perform a simulation of flow over a commercial aircraft. One of such commercial aircrafts operating on this Chennai-Bangalore corridor is the Airbus A320. This simulation is performed by the aid of computational fluid dynamical software such as ANSYS CFX. In computational fluid dynamics, basically an iterative code is used to solve various fluid dynamical equations, mainly the Navier-Stokes equation, as well as other heat and mass transfer equations using boundary conditions which are input to the software by the user. A 1:33 scaled model of the Airbus A320 aircraft is used to analyze flow under ambient conditions. One of the models which are used to estimate the type of flow and the various features is the K omega SST model, which is coupled with a high turbulence intensity profile, and it is identified as the most suitable equation to analyze flow around the plane. The result of the CFD analysis performed are depicted here in these two figures. To the left, we observe the top view of the aircraft, and to the right, the bottom view. Here, it is very clear that the greens are of a higher pressure gradient, whereas the blues follow a lower pressure gradient. Since the aircraft has to maintain a stable flight in the air, it makes sense that there is a higher pressure underneath the aircraft, that is below the wings, and a lower pressure above. Uh, this difference is observed clearly and is the reason for flight, as shown. During in-cloud turbulence, especially during the stages of takeoff and landing, uh, high instability is created inside the flight, uh, resulting in a sudden increase in engine power required to maintain equilibrium or to get back to equilibrium stage. This leads to an increase in fuel consumption at that moment, and this is more so especially in in a monsoon-driven country such as India, where there is a high in-cloud turbulence observed. This turbulence is characterized through large eddy simulations, which are showcased in the following slides within the cloud. For this stage of the study, we use the UK Met Office large eddy model to compute large eddy simulations in order to determine the vertical velocity perturbations within a cumulus cloud, which is the most common cloud present at the particular height during takeoff and landing stages of the flight. Two different days in Chennai city are examined, one during a normal condition, a regular day, and another during extremely turbulent conditions such as during a cyclone. The results of the large eddy simulation performed using this model are showcased in these two images shown here. To the left, we observe the vertical velocity perturbations for a regular day, while on the right we observe the same for the cyclone Neelam. Here we see that the range for the updraft is much larger in the case of the cyclone, which is about 2 kilometers, whereas it is only about 20 meters or so in for a regular day. The vertical velocity perturbations are consequently much lower for a normal day where there is less turbulence, and this is characterized by about 1.4 meters per second, whereas it is much higher, up to 2.5 meters per second during the cyclone Neelam. Now there are some concerns for this present route that we are observing here. The total flight time, as mentioned earlier, is 45 minutes, and the time spent during ascent and descent, that is during takeoff and landing stages, is about 20 minutes or so. The aircraft spends most of this flight time passing through these examined cumulus clouds and the vertical velocity perturbations during turbulence, observed during turbulence, and these exist at a height of about 2000 to 5000 meters or so. Variously sized aircraft experienced different degrees of turbulence due to these low-lying clouds. Sudden pressure change due to the vertical velocity perturbations may cause a loss of lift within a very short span of time, which is characterized by a very quick turbulent drop observed in most of the flights which you may have taken. This degree of downward acceleration, or to give it its formal term, the incremental vertical acceleration, exemplifies the effect of turbulence on passenger comfort within the aircraft. This is examined further in the following slides. The incremental aircraft vertical acceleration, given in units of g, that is the acceleration due to gravity, is calculated for both weather conditions seen previously for two differently sized aircraft, one a Boeing 737-800, which is a medium-sized aircraft, and the other an ATR-72, which is a small-sized aircraft. It is important to note that the degree of vertical acceleration has a direct dependence on the gross weight as well as the wing area, which are characteristics that differ completely for various aircraft. The following equations shown here depict the calculations which are shown for clarity in the next slide in the table. The term we are primarily concerned about is delta AZ, which is the incremental vertical acceleration given in units of g. This is calculated for both the Boeing 737 as well as the ATR-72 during regular and stormy days. The various other factors and terms are defined clearly, and the values have been taken after detailed calculations which are not mentioned here for the sake of shortage of time. There are a lot of implications of performing this calculation. The The maximum vertical velocity perturbations discussed earlier, that is 1.4 meters per second as well as 2.5 meters per second for regular and stormy days, have been plugged in to find the maximum incremental vertical acceleration, that is delta AZ, for both these days. These are found to be less for a Boeing 737 as compared to an ATR 72 for the same maximum updraft discussed previously. According to turbulence indicators, it is seen that it was seen that the Boeing 737 experienced a comfortable flight on a regular day, whereas the ATR 72 experienced a moderate degree of turbulence. During the cyclone Neelam, however, the Boeing 737 experienced a moderate degree of turbulence, while the ATR 72 experienced severe in-flight turbulence. Uh, from this calculation, it is concluded that a heavier aircraft experiences a lesser degree of turbulence and should be preferred to ensure that passenger comfort is given a high priority, especially over busy routes such as the Chennai-Bangalore corridor. In this slide, we show the various low-cost domestic carriers operating along this route, as well as the various types of aircraft operated by them. The frequency of these flights are also mentioned here. As we can see, aircraft type 1, which are medium weight aircraft, can replace larger number of lightweight aircraft in order to ensure that the aviation related parameters are influence the EVI indicators in a lesser way. This enhances passenger comfort as well as reduces the environmental vulnerabilities of both the cities in question. The other benefits of using larger sized aircraft is that large aircraft have lower environmental per passenger kilometer costs than smaller aircraft. For instance, we take the case of replacing a number of ATR 72s with a proportionate number of Boeing 737s. From the literature available, it was estimated that the CO2 emissions from aviation fuel is estimated to be 3.15 grams per gram of fuel. By performing a calculation based on the number of seats present in each aircraft, it was determined that about 5 ATR 72s, which are the smaller size aircraft, can be replaced with 4 Boeing 737 by the low cost carriers. Now that we have concluded that using a heavier aircraft has better consequences for the environmental vulnerabilities of both the connected cities, we try to quantify this by determining factors which help the selection of the aircraft type and weigh them against the final EVI values which have been obtained previously using the previous calculations. This is done in order to quantify the benefits of using larger aircraft in place of lighter ones, as seen in the following slides. In this slide, we observe the various aircraft factors such as carbon dioxide emissions, incremental aircraft vertical acceleration, travel time, airport congestion, as well as aircraft noise, and how they are impacted by using a lightweight aircraft, which is the type 1 mentioned here, and medium weight aircraft, which is the type 2. The final values impacted on all these aircraft factors is summed up, and these final values are to be multiplied with the final scaled EVI values obtained previously for both the cities. Once we have done this multiplication, we observe that the EVI of Chennai is about 226.53 when lighter aircrafts are in use, while it is only 151 or so when a medium-sized aircraft is in operation for this route. Similarly, a higher value for the EVI is observed for Bangalore while using lighter aircraft, whereas while using heavier aircraft, this EVI value drops considerably. Thus, this type of quantitative approach verifies the need for choosing to operate the right aircraft type while incorporating the social benefit of human comfort for the passengers who are frequently traveling along this route. There are a number of wider implications of this present study. There is a need to prescribe vulnerability values for specific need-based environmental situations, such as air travel between two connected cities anywhere around the world. Uh, there is also it is also seen that vulnerability should not be limited only to the physical environment. Overall comfort is extremely important, especially in the case of the aviation industry. Also, the telling novel EVI calculator depicts visual imagery of using icons which will appeal to users in the aviation industry all around the world. While this is a particular case study, only to two connected cities between Chennai and Bangalore within India, the mathematical framework and the application methodology is transferable to any two connected cities all around the world. Hope you enjoyed this presentation. Thank you very much for listening.